I'm looking at the document file, the docx file for module 4. And last time in the last video 4b, we looked at the Fourier series, which says that any repetitive shape, and it has to be a repetitive shape, any repetitive shape can be built up from sinusoids. This was the equation, the Fourier series, built up from sinusoids, and only the harmonics are required. Only integer multiples of the fundamental frequency are required. But the question is, what if the shape doesn't repeat? What if the function is non-repetitive? For example, a single square pulse rather than a repetitive square, rather than a square wave that repeats itself. So we want to know what a single square pulse, what frequencies are needed to build up a single square pulse. Now this is more difficult because the sinusoids have to add to zero. They have to cancel out on either side of the pulse. But the answer is it can be done with sinusoids, but you need all frequencies and not just the harmonics. So for a non-repetitive shape, you need all the frequencies, and then we call it a Fourier transform. If the shape is repetitive, then you just need particular frequencies, the harmonics, and we call it a Fourier series. So Fourier series or Fourier transform, it's like going from a summation to an integral. Fourier series, you're only using particular frequencies, and in a Fourier transform, you're using all the frequencies. So if we look at this diagram here, which is figure 4 in the book, the chapter, and we look at a single square pulse. So these are non-repetitive shapes, a single square pulse, an image, that gets brighter. It's a stripe, let's say, in a two-dimensional image. The frequencies that are needed to build up that pulse are shown here. Now, these are spatial frequencies. This is positive. This is negative, although there are no negative frequencies. But mathematically, we show it like this here. The frequencies that we need are not just particular harmonics. You need all the frequencies here, all the frequencies, a whole continuous stream of frequencies, mostly low frequencies, but the height of this here gives how much of a particular frequency you need in order to build this up. You need less and less. It goes to zero here, and then you subtract frequencies here and add frequencies there, and this is the shape of the Fourier transform then. The envelope of this here gives the amount of sinusoids that are needed to build this up. And it's continuous, so it's an integral really. It's a lot of contributions, but they're infinitely close together. This is a standard shape. We're not going to do a lot of the math of Fourier transforms. We're going to think about them in terms of shapes. So a single pulse, the Fourier transform of it is, we're going from the spatial domain to the frequency domain. The Fourier transform has this shape, and this shape is a sinc function, S-I-N-C, a sinc function, which is a sinusoid divided by a number. So it's like a sinusoid, but it gets smaller and smaller the further that you go out here. So this is a sinc function. The Fourier transform of a square pulse is a sinc function. The other thing about Fourier transforms we'll see is that the inverse Fourier transform, that is going back from here to here, is practically the same thing. There's a difference of a little minus sign in the exponent, but a Fourier transform and an inverse Fourier transform are practically the same. So that if you had a pulse shaped like this, shaped like a sink function, so you've got a stripe, but it blurs out, it gets less intense as you go out, and then it comes up again. It has a shape like this here. If you have a sink pulse, then the Fourier transform of that is a rectangular function. That is, in order to build this up, you need all the frequencies here up until a certain number, all the frequencies and equal contributions from each of them. And the number here is related to the width of the sink function, inversely related. So if this is A, that is the sink function has a width 2A, in the spatial domain, then this cutoff point in the spatial frequency domain is 1 over 2A, 1 over the width of the pulse. We saw it here, A, and this is 1 over A. So there's an inverse relationship between numbers in the spatial domain and the numbers in the frequency domain. But a square pulse gives a sink, and therefore a sink, the Fourier transform of it, will be a square pulse. If we look at these two here next, these are cosine and sines, and we know they're perfect basis waves. So the Fourier transform of them, depending on the distance between the peaks here, the Fourier transform will be a spike at the inverse of that distance. This distance is 2A. The corresponding frequency will be 1 over 2A. Same for a sine and a cosine. There's also a redundant twin here, but this is minus frequency, so this is a bit weird. We don't generally look at amplitudes. This is the amplitude here in the frequency domain. We look at intensity, the square of these. So in that case, this would be positive 2 if we were to look at the intensities. And what we'd see, the Fourier transform of a sine or a cosine would be 2 spots, 2 sharp peaks. A peak, this is the center of the Fourier transform plane. We'd see a spot here, and we'd see a redundant spot, same distance to the other side. So bear that in mind, and we'll see that in practice later. The other shape that's interesting is the Gaussian. If we have a Gaussian pulse, the Fourier transform, if we do the math, but we're not going to do the math, but if we put it into the Fourier transform equation, a Gaussian, the Fourier transform of a Gaussian is another Gaussian of width equal to the inverse of the width of the Gaussian from which it came. So a wide Gaussian gives a narrow Gaussian, gives a narrow range of frequencies required to build up a wide Gaussian pulse, and vice versa. A narrow one here would need a wide range of frequencies. If we continue that thought, a narrow pulse here in the spatial domain requires a wide range of frequencies here. if we keep narrowing this down, narrow this pulse down, down, until it becomes infinitely narrow, that is a delta function, infinitely narrow, then the Fourier transform, this Gaussian has got wider and wider until it becomes infinitely wide. That is, to build up a spike, a delta function in the spatial domain, you need all the frequencies of sine waves, all the frequencies, and equal contributions from them all. Now, last in this here, and you can read up a little bit about it in the book, last is this one. What's the Fourier transform of a triangular shape? If we have a triangular pulse in the spatial domain, what are the frequencies that we require to build it up? And a triangle in the spatial domain, we've seen we can get a triangle from convolving a square with another square in the spatial domain. Square convolved with square gives you triangle. And the Fourier transform of a square is a sinc function. You know, we've got a square convolved with another square, each of them giving sinc functions, each of them convolved with each other in the spatial domain. But in the frequency domain, the convolution operation becomes a regular multiply. So you get the sinc function from one of these squares. It's not convolved, but it's multiplied by the other sinc function. So the Fourier transform is a sinc squared. Fourier transform of a triangle is a sinc squared function, where there are no negative parts to it, and they get smaller and smaller much more rapidly than the sinc function does. So I want you to finish reading that section in the book, section 7.2, including figures 7.6 to 7.12. Think about them, read about them, and complete section 7.2. Now, if we go to the book and go to Appendix A of the book, there is some of the mathematical detail, which I want to skim over and not look at in at great detail. But the Fourier series is here. It's a sum of sines and or cosines. We can combine the sines and cosines together to give a complex exponential, where j or I is the square root of -1. And we can do that because combining cosines and sines, e to the j theta is a cosine plus j sine theta. So we can shorten the sum of sines and cosines to just give us a sum of exponentials, a sum of complex exponentials. And we move on to the next page in this here. You know, what is a complex number? A complex number, C, can be made up from a real and an imaginary part. So we can draw it like this. The real part is A and the imaginary part is B. And C is equal to A plus JB, where again J is the square root of -1. So this is a complex number, and we've just seen we've got a complex number here. The Fourier series can be a series of complex exponentials as a shortcut for writing sines and cosines. And we can look at the real and the imaginary parts, or we can look at them as rather the magnitude of this vector here from the origin to the point C. The magnitude of that will be from Pythagoras, just the magnitude squared will be a squared plus b squared. The magnitude will be the square root of a squared plus b squared. So we can have a magnitude and we can have an angle here, which we'll call a phase. So often, instead of just looking at a complex number as a real plus an imaginary part, we look at the complex number as having a magnitude and a phase. Now, if we move from the Fourier series to the Fourier transform, we said the Fourier transform requires all the frequencies, not just the harmonics. So the Fourier transform is an integral over all the frequencies instead of a sum over all the harmonics. And this is the equation for a Fourier transform. This is the signal, the function, the image, and this is its Fourier transform. Where this also, if we follow the math through, I'm not going to do it, this is given by this here. It's related back to the function itself with the same complex exponential, except there's a minus sign in here. And that's why I say the Fourier transform and the inverse Fourier transform are practically the same thing. You know, if you have a square pulse and it gives a sinc function in the Fourier domain, the frequency domain, its Fourier transform is a sinc. Then if you have a sinc pulse in the spatial domain, it Fourier transforms to a square pulse in the frequency domain. Keep that in mind, and also this idea of magnitude and phase. And in the next video, we'll look at some images in image J and look at their Fourier transforms.